In this lecture, we're going to be going over the basics of circular motion and, more importantly, the kinematics of circular motion. So let's go ahead and let's consider. There are actually three types of acceleration. And hopefully you're sitting there saying to yourselves what those three types are. There's speeding up, slowing down, and there is changing directions. If any of these three things are happening, then there must be acceleration. And if there is an acceleration, either speeding up or slowing down or changing directions, then we know that there must be a net force that exists to cause that acceleration. Or another way of saying it is there must be, the acceleration is equivalent to the net force over the mass of that object. And so we know that that has to happen and that has to be true. Absolutely nothing about what we're analyzing has changed as far as that perspective. So good news, we're not learning a brand new concept. We're just applying things that we know. We're applying the physics that we're learning to this concept of circular motion. So that means that circular motion really isn't any different than any other type of kinematic motion. So we're going to use the kinematics that we know, and we're going to be using the force concepts that we know in order to solve problems of circular motion. So that means that the concepts and the terms uniform motion and uniform accelerated motion are still going to apply. And if these two concepts apply, then we're going to be looking at Newton's first and Newton's second law and how they apply to circular motion. So, uniform motion. Let's go ahead and let's make sure that we're warm and fuzzy with uniform motion. Uniform motion is traveling along a straight line path with constant velocity. You're going to notice that I underlined straight line path because you have to be traveling in a straight line in order to not be changing directions, because changing directions is an acceleration. So uniform motion, which we've called up to this point UM, is constant velocity. Velocity is a vector, so we're talking about constant magnitude and direction there. So objects that travel in a circle don't travel in a straight line, and so they aren't experiencing uniform motion, right? A circle looks like this. Alright, which means that an object right here would be traveling in that direction. An object right here would be traveling in that direction. An object here would be traveling in that direction. And around and around and around. So even if the speed stays constant, the direction of that velocity vector is constantly changing. So this type of motion right here is not uniform motion. We will not be looking at constant velocity values. So we say that they're experiencing uniform accelerated motion. That change in directions requires that we accept an acceleration is occurring. So constantly changing directions means constantly accelerating. If they are accelerating, then they are experiencing a net force. And that net force must be in the same direction as the acceleration. Right? This is a convenient thing to consider here because nothing about this is any different than what we've experienced up to this point in time, right? That net force and that acceleration are both vector values, right? And since they're both vector values, and you know that the net force must be in the direction of the acceleration, you know that they have to be pointing in the same direction. So if we can determine the direction of acceleration, then we can also determine the direction of the net force, and that's going to be really nice for us when we're resolving our free body diagrams and finding net forces. So let's go ahead and let's take a look at this. So we can consider changes in instantaneous velocity to determine the magnitude and direction of acceleration. Right, so another way of saying that is at any point in time, the acceleration of an object, whether it's instantaneous or constant, please remember that for the most part we only accept physics of constant acceleration. So in all of the physics that we've done up to this point in time, the instantaneous acceleration and the average acceleration are the same. For the most part, we're going to be keeping that rule the same. But that acceleration is going to be equal to the change in velocity over the duration of time that change occurred. All right, this is our kinematic equation for acceleration. So, acceleration occurs when the magnitude of velocity changes. It also occurs when the direction of the velocity is changing. So magnitude of velocity for circular motion, we're going to start by considering a constant magnitude. Right, so that means if the velocity started at 5 meters per second, the velocity will also end at 5 meters per second. But if the object is traveling with this concept of circular motion, then we know that it's accelerating, because in order to travel in a circle, you have to constantly change directions. That's why going in a circle makes you feel dizzy. Your body has no ability to sense how fast you're going if you don't have any perspective. However, your body can sense acceleration, and that acceleration is the sensation that makes you feel dizzy. So, the acceleration that occurs in this circular motion is occurring, and it's only causing the object's direction to change. So this situation, right, an object's traveling in a circle, the magnitude of the velocity is constant, direction is changing. We're going to call this uniform circular motion. So hey, new abbreviation, UCM. Uniform circular motion, which has its own rules. Remember, uniform circular motion is still an accelerating situation. It's just uniform circular acceleration. It's just a type of uniform accelerated motion. The speed is constant, and notice most of the time we write velocity as v. But if we're referring to speed, this is a scalar quantity. Velocity is a vector quantity. So there's our little vector symbol that we put above it. The speed, the magnitude of the velocity in this situation is considered constant. So the speed is constant. A change in direction is the only thing that's occurring for uniform circular motion. And so this is the concept that we're going to be looking at. And we're going to actually derive a specific way to calculate the acceleration of objects experiencing uniform circular motion, or UCM. So the speed is constant. That's that v without the vector value. We're going to talk specifically about how vectors work when we're looking at uniform circular motion. So let's go ahead and let's focus in on our kinematic equation for deriving acceleration. Acceleration equals change in velocity over time, and this could be any chunk of change in velocity over time, because we're still only considering situations in which acceleration is constant. So v2 minus v1, or v minus v naught over the change in time. A lot of the times we set that initial time to 0. And it's really easy for us to consider this for something that has a change in magnitude of velocity. But here we're dealing with a situation where the magnitude isn't going to be any different. So that means the magnitude of v2 could be 5, and the magnitude of v1 could be 5, but we're still going to get an acceleration. And the only way to consider that is to consider both of these velocities as vector quantities. So consider in this beautiful picture of a circle I have right here. All right, here's a beautiful, perfect circle. And we're considering the point right here, point A, where the velocity is pointing in that direction. And a vector right here at point B, where the velocity is traveling in this direction. And the magnitude of these two velocity vectors is exactly the same. We're going to say that from v1 to v2, there's this, it travels this tiny little arc length right there called L. And if we compared that to the radius, right, which we call point C here, it would be that angle theta. That's going to be important for just the derivation of the equation. But here's the thing. If we look at the difference between v1 and v2, you notice that this arrow points straight down. Right? And that's important because that arrow right there actually points straight toward the center of the circle, or radially along the circle. And you can do this for huge chunks of the circle, or you could do it as this area gets smaller and smaller and smaller. One of the reasons that we want to look at this as we approach smaller and smaller and smaller changes in velocity is because as the change in time gets smaller, or we're looking more at an instantaneous value, so does the arc length also get smaller. And the smaller the arc length gets, the closer it's going to be to a perfect triangle, this perfect triangle to be specific. So here you can see I have this triangle A to B to C, where we say that here's theta and here's that arc length. And remember, as we make this portion smaller and smaller, this arc length gets closer to that perfect triangle. And that makes this a similar triangle to the difference between these two velocities. And that means that that angle right there is also going to be the same. So these become similar triangles. For an instantaneous velocity, remember magnitude-wise, v1 and v2 are 0. So that means that for similar triangles, if we compared the radius and the arc length for this, where this is the radius, to the change in velocity versus one of those velocities, you know that for similar triangles those would be equivalent ratios. Doesn't matter if one's larger or smaller than the other. If the angle is the same, then those ratios remain the same. And that means that if I solved this equation for delta V, then I'd get V over R times L. That's what delta V equals, and we used a mathematical proof of similar triangles to show us that. And since we know that acceleration equals change in velocity over time, I can plug in this value right here as the delta V here. I do that in a little bit of algebraic manipulation. V over R, and I put this L over the T. I could do that because order of operation allows it. V over R is just velocity divided by radius. L over T is this path length traveled on a triangle. It travels this much distance in that much time. So this is actually just a linear velocity displacement over time. So that means that I could actually substitute for L over T, I could substitute another velocity. And when I do that, I get that the acceleration for an object traveling with constant velocity in a circle where the direction is constantly changing is going to be equal to the squared linear velocity divided by the radius of the circle. And that's it. That's how you get acceleration for an object traveling in a circle. This gives us the magnitude of circular motion's acceleration, which you'll see sometimes abbreviated as AC, centripetal or center-seeking acceleration, causing it to constantly travel in a circle and change directions. That centripetal acceleration, AC, is equal to v squared over r. This will always be true for uniform circular motion. The direction is always toward the center of the circle or along the radial pathway. Because it's along the radial pathway or pointing down the radius of a circle at any given point in time, sometimes that AC you'll see written as AR for radial acceleration. Both are totally acceptable terms, AC versus AR. You don't have to worry about which one you want to use. They're the same thing. But this is the equation for circular motion. If you're calculating acceleration for uniform circular motion, this one's always going to work, which is kind of nice. So let's go ahead and let's consider vector quantity still. For all uniform circular motion, the velocity is constantly changing, but the speed, the magnitude of the velocity, is constant. So when we look at an object as it travels around a circle, here I've got a couple points, right? At this point in time, if we looked at that instant, right, what direction the object is traveling, its velocity vector would be pointing just tangential to the circle. Right here, if we considered it there, it's traveling in a slightly downward direction, so that velocity would be pointing just like that. And for this point right here, all right, at that instant, the velocity would be traveling at that tangent to the circle. Right? And that's going to be true all the way around. You notice that while the magnitude of that vector doesn't change, the direction that it's pointing or the direction that it's going is changing. So that means that at every single instant around a circle there is acceleration. It's called centripetal or radial acceleration. So that means that I can actually find the direction of the acceleration at any point along the circle as radial, pointing toward the center of the circle along the radius. And that's going to be true. You notice that those acceleration vectors are changing too, but the magnitude of that acceleration is never going to change. And if we establish, as far as the direction goes, if we say center of the circle is positive, then we could say, hey, the magnitude and direction of that acceleration are constant. So, velocity is measured instantaneous, right? Each one of these is an instantaneous velocity vector with the same magnitude. The instantaneous velocity will always be tangent to the curve, and so you can always find it by drawing a line tangent to the curve of the circle. That tangential velocity is a vector quantity, and so never forget to treat it as such, even though you're using the magnitude as a scalar. And that's true for any amount of motion that has any curve to it. So this will work for complete circles for uniform circular motion. It will also be true for projectile motion, right? Anytime you're traveling along a path, as the velocity changes and the direction of the velocity changes, you can find that that centripetal acceleration will point radially down the center of the circle. And this is also true for satellites or anything orbiting out in space. So there's a whole slew of concepts and problems that you can apply uniform circular motion to. But there's a few terms that we're going to go over that you need to make sure that you're warm and fuzzy with if you're going to be doing circular motion problems. And hopefully they're not brand spanking new terms, but they are frequency and period. Frequency just refers to how often a repeating event happens. So for a circle, the frequency would be how often that circle occurs for a traveling object. It's measured always in revolutions per second or repetitions per second. And you could see that this is a per second, so that means that time is in the denominator. So 10 revolutions per second would be an example of a frequency. Revolutions isn't actually a unit, so it gets dropped out. And so you could say that this is happening 10 per inverse second, or 10 per second. Or what you're going to most oftenly see is 10 hertz, because hertz, Hz, is what an inverse second is equal to. Hertz is a lot easier to say than inverse seconds. So frequency is how often a repeated event happens. Period is the time it takes for one revolution or one repetition to happen. Period is a time. It's not a per second. It's a time itself. So that means that the unit for a period, which is given by the symbol t, is a second. All right. So if the wave took 10 seconds to travel one cycle, right? If it was a wave, and that one cycle took 10 seconds. If it's a circle, right, it took 10 seconds to complete its motion in a circle. That means that the period would be 10 seconds. Now you notice this one is a second, this one is an inverse second, so it tells you that there's this relationship between period and frequency, and you're just going to have to commit this one to deep down in the depths of your heart, because period and frequency have an inverse relationship, which means that the period is equal to the inverse of frequency, or the frequency is equal to the inverse of a period. So if you know one, you may solve for the other, and you can always do this. This will always be true. And if you're ever stuck on what to do, always check the units. Since the units are inverse to one another, it tells you if you've been given a period or frequency. Now, sometimes periods and frequencies are given in values other than seconds or hertz. If you receive a period in days, turn it into seconds. If you receive a period in years, turn it into seconds. Anything that's not in seconds, turn it into seconds, and then you can either get the period or the frequency from it. We're going to be using these a lot for circular motion. Let's take a look at how period and frequency are useful for circular motion. Both period and frequency are some sort of measure of time. And you know that time is a critical value to kinematics, right? Time and kinematics. I can think of several kinematic equations that have time as a variable. So if you know the period or the frequency, then you might actually have some information for solving some kinematic equations. Like the equation for calculating speed and tangential velocity are the same. All right? Remember that the speed, or the non-vectorial value of velocity, is typically a constant value for uniform circular motion. But tangential velocity will have the same magnitude. It just happens that we would know the vector direction as it traveled along a circle, right? So right at that point in time, maybe the value is 2 meters per second. And then that would be the speed of an object traveling in a circle. The tangential velocity would still be 2 meters per second. It just means that at that particular time that we're looking at it, it's traveling in that tangential direction. But here we look at it. The tangential velocity, or speed, is calculated as velocity equals 2 pi r over the period of the circle. So where the heck does this equation come from? Well, I'm going to tell you, just to cheat, velocity equals change in position over time, right? Well, the time is the period, and the period is the time it takes it to get all the way around one complete revolution. Right? So if we're saying that the time is the period, then we must be saying that the change in position is how long the distance it took to get all the way around a circle. So if we weren't looking at tangential velocity, then we would know that the displacement of that situation was 0. But since we are looking at the speed, or the temporary tangential velocity, we can actually look at the scalar quantity of how far did it travel in that one period. Well, it traveled the perimeter, or surroundings, of a circle, which is the circumference, and the circumference of a circle is 2 pi r. So that means that in order to calculate the speed of an object traveling around a circle, you get circumference divided by period, or 2 pi r over t. And since 1 over t is equal to frequency, we can just easily substitute, and we could also say that velocity is equal to 2 pi r times frequency, which is pretty clever if you ask me. So we're going to take a look at how to use these values to calculate the moon's centripetal acceleration. The first thing to consider is a few values. So the moon orbits Earth. If we imagine this is Earth, there's a good looking Earth, and this is moon, not to scale. And the radius of orbit is right there, and everything in space travels counterclockwise. So the moon's going like that. We know that the radius is 38,400 kilometers, and we know that it takes the moon 27.3 days to make it one complete orbit around the Earth. If you ever want to check that, please take a note of what phase the moon is in when you look at it. Count 27.3 days later, look up in the sky, and the moon will be the exact same shape and exact same phase. So we're going to determine the centripetal acceleration, or the acceleration of a moon traveling in a circular orbit around the Earth. In order to do this, we're going to assume that its path is completely circular, and we're going to assume uniform circular motion. If I assume uniform circular motion, then I know that the acceleration will be equal to v squared over r. And since I know that this object is traveling in a circle, and we're assuming uniform circular motion, so we're assuming a constant speed, then I know that velocity is going to be equal to 2 pi r over t. Now, I can't plug in this radius, and I can't plug in this period, and if you ask me why, then I'm going to say for shame, because when you look at those, you should notice that neither of them are in SI terms. So 38400 kilometers is actually supposed to be 38400,000 meters, or 3.84 times 10 to the 7th meters. And this period, 27.3 days, we need to change it into seconds. 27.3 times 24 hours in a day times 3,600 seconds in an hour. That's actually 2358720 seconds. Now, I can plug in this radius straight down here, and I can plug in this period straight here, so why don't I solve for velocity? Velocity equals 2 pi times 3.84 times 10 to the 7th meters divided by 2358720 seconds, and I will get a value in meters per second. So it's going to be 384,000,000 times 2 times, where's my pi on? There it is, pi, divided by 2358720 is going to be equal to a velocity of 102.3 meters per second. I'm keeping a few extra significant figures here. I will ultimately report my value to 3 significant figures. Now I have this velocity. I'm going to plug it into centripetal acceleration. AC is equal to 102.3 meters per second squared over the radius 384 times 10 to the 7th meters, and I get squared divided by 384,000,000 equals, I got 2.72 times 10 to the negative 3rd meters per second squared. Now, that's our acceleration of the object around the moon, or how fast it's changing, or the moon around the Earth. That's how fast it's changing directions, or it's accelerating. In terms of g's, I'm just going to take that number and I'm going to divide it by 9.8, and I get, in terms of g's, I get 2.78 times 10 to the negative 4th g's. Now please note, this is not the acceleration due to gravity of an object on the moon. This is the acceleration of the moon around the Earth due to Earth's gravitational pull on the moon. So that's how you're going to be using these values of frequency, period, and centripetal acceleration, and this clever way of calculating the velocity or tangential velocity or speed of an object traveling with uniform circular motion. So that's it. That's the kinematics of circular motion. You're still using change in velocity over time for acceleration. You're still using displacement over time for velocity. And the only difference now is you're considering uniform circular motion, or a situation where you can assume that an object is traveling in constant speed in a perfect circle.